National Electrical Code Section 250.52 A4 states that electrodes shall not be connected to the neutral conductor of a grounding system. Section 250.52 A7 states that electrodes shall not be connected to the grounding conductor or equipment grounding conductor of a branch circuit or feeder. Institute of Electrical and Electronics Engineers Standard 1100-2018 Recommended Practice for Powering and Grounding Electronic Equipment. Section 2.33.1 states that driven steel pylons are not recommended as a sole means of grounding due to the possibility of a non-conductive coating forming on the pylon resulting in higher resistance. Additional considerations include the fact that driven steel pylons can experience corrosion over time, which can reduce their conductivity and effectiveness as grounding electrodes. The non-conductive coating referred to in Institute of Electrical and Electronics Engineers 1100-2018 can result from oxidation or other chemical reactions on the surface of the pylon. Relying solely on driven steel pylons for grounding can increase the risk of electrical shock or damage to equipment in the event of a fault or overvoltage. It is not recommended to use driven steel pylons as the only grounding means in a building. Instead, a combination of multiple grounding electrodes should be used, such as concrete-encased electrodes, ground rods, and connections to metal water pipes in building steel. Grounding is a critical aspect of electrical safety, protecting both people and equipment from hazards. The National Electrical Code, or NEC, and standards such as Institute of Electrical and Electronics Engineers 1100 offer guidelines for establishing effective grounding systems. Understanding these standards is essential for electrical engineers, contractors, and anyone involved in electrical installations. A grounding system provides a low-impedance path for fault currents to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly interrupt the circuit and prevent electrical shock or damage. The NEC outlines acceptable grounding electrodes in Section 250.52, including metal underground water pipes, metal frames of buildings or structures, concrete-encased electrodes, ground rings, and ground rods and pipe electrodes. Each of these electrodes has specific requirements for installation and sizing to ensure its effectiveness. While steel pylons might seem like a convenient grounding solution, they often present challenges due to the potential for corrosion and the formation of non-conductive coatings. Institute of Electrical and Electronics Engineers Standard 1100, which provides recommended practices for powering and grounding electronic equipment, specifically advises against using driven steel pylons as the sole means of grounding. The NEC also emphasizes the importance of bonding all metal parts that are likely to become energized to the grounding system. This includes metal enclosures, raceways, and equipment frames. Bonding ensures that all these metal parts are at the same potential, minimizing the risk of electrical shock. The grounding electrode conductor, or GEC, connects the grounding electrode to the equipment grounding bus in the service equipment. The size of the GEC is determined by NEC Table 250.66 based on the size of the service entrance conductors. Proper sizing of the GEC is crucial for carrying fault currents safely back to the source. In addition to the grounding electrode system, the equipment grounding conductor, or EG, provides a path for fault currents from equipment back to the service equipment. The EGC can be a wire, conduit, or other approved metal raceway. Its size is determined by NEC Table 250.122 based on the rating of the overcurrent protective device protecting the circuit. Effective grounding systems require regular inspection and testing to ensure their continued performance. Ground resistance testing can verify the effectiveness of the grounding electrodes, while visual inspections can identify any signs of corrosion or damage to the grounding conductors and connections. When designing a grounding system, consider the specific requirements of the installation, including the type of equipment being used, the soil conditions, and the potential for corrosion. Consulting with a qualified electrical engineer or contractor is essential to ensure that the grounding system meets all applicable codes and standards. Grounding systems are not static installations and require maintenance and periodic testing. Corrosion, loose connections, and physical damage can compromise the effectiveness of a grounding system over time. Regular inspections can identify these issues and allow for timely repairs or replacements. Ground resistance testing is a common method for evaluating the effectiveness of a grounding system. This test measures the resistance between the grounding electrode and the earth, providing an indication of how well the grounding system can dissipate fault currents. High ground resistance can indicate a problem with the grounding electrode or the connections to it. The NEC and Institute of Electrical and Electronics Engineer standards provide guidelines for acceptable ground resistance values. Soil conditions can significantly impact the effectiveness of a grounding system. Soil resistivity, which is a measure of the soil's resistance to electrical current, varies depending on factors such as moisture content, temperature, and chemical composition. High soil resistivity can make it difficult to achieve a low impedance ground path. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or ground enhancement materials to improve the effectiveness of the grounding system. Ground enhancement materials are substances that are added to the soil to reduce its resistivity and improve its conductivity. These materials can include bentonite clay, gypsum, and various chemical compounds. When using ground enhancement materials, follow the manufacturer's instructions and ensure that the materials are compatible with the soil conditions. Corrosion is a major concern for grounding systems, especially those that are buried underground. Corrosion can weaken grounding conductors and connections, reducing their ability to carry fault currents. To prevent corrosion, use corrosion-resistant materials such as copper or stainless steel for grounding conductors and connections. Also, consider using cathodic protection, which is a technique that uses an electrical current to suppress corrosion. Lightning protection systems are designed to protect buildings and equipment from damage caused by lightning strikes. These systems typically include air terminals, down conductors, and a grounding system. The grounding system for a lightning protection system must be separate from the grounding system for the electrical power system. The NEC and Institute of Electrical and Electronics Engineer standards provide guidelines for designing and installing lightning protection systems. Surge protective devices, or SPDs, are used to protect sensitive electronic equipment from voltage surges caused by lightning strikes, power line disturbances, or other events. SPD are typically installed at the service entrance and at branch circuit panels. The NEC requires that SPD be properly grounded to provide an effective path for surge currents. In addition to the NEC and Institute of Electrical and Electronics Engineers standards, other organizations such as Underwriters Laboratories, or UL, and the International Electrical Testing Association, or IETA, provide standards and certifications for grounding equipment and practices. Following these standards and certifications can help ensure the safety and reliability of grounding systems. Grounding is not just a matter of meeting code requirements. It is a fundamental aspect of electrical safety that protects people and equipment from harm. By understanding the principles of grounding and following best practices, you can create safe and reliable electrical systems. Grounding electrodes must meet certain requirements to be effective. For example, ground rods must be at least 8 feet long and driven into the ground to a depth of at least 8 feet. Metal underground water pipes can be used as grounding electrodes, but they must be in direct contact with the earth for at least 10 feet. Concrete encased electrodes, also known as UFO grounds, must be encased in at least 2 inches of concrete and be located within the bottom 20 feet of a concrete foundation or footing. The grounding electrode conductor must be properly connected to the grounding electrode. The connection must be made using approved methods such as exothermic welding or listed connectors. The connection must also be protected from corrosion and physical damage. Equipment grounding conductors must be properly sized to carry fault currents. The size of the equipment grounding conductor is determined by NEC Table 250.122 based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. Bonding is the process of connecting all metal parts that are likely to become energized to the grounding system. Bonding ensures that all these metal parts are at the same potential, minimizing the risk of electrical shock. Bonding can be accomplished using bonding jumpers, bonding bushings, and other approved methods. Ground fault circuit interrupters, or GFCIs, are devices that protect people from electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas. GFCIs should be tested regularly to ensure that they are functioning properly. Arc fault circuit interrupters, or SIs, are devices that protect against fires caused by arc faults. Arc faults are unintentional electrical discharges that can occur in damaged or deteriorated wiring. SIs are required in certain locations, such as bedrooms and living rooms. SIs should be tested regularly to ensure that they are functioning properly. Electrical safety audits can help identify potential electrical hazards and ensure that electrical systems are in compliance with applicable codes and standards. Electrical safety audits should be conducted by qualified professionals. Electrical safety training is essential for all workers who work with or around electrical equipment. Electrical safety training should cover topics such as grounding, bonding, lockout-tagout, and personal protective equipment. Lockout-tagout is a procedure that is used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout-tagout involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch. Personal protective equipment, or PPE, is used to protect workers from electrical hazards. PPE can include items such as rubber gloves, safety glasses, and insulated tools. Working with electricity can be dangerous, but by following safe work practices and using appropriate safety equipment, you can minimize the risk of electrical shock and other electrical hazards. Always de-energize electrical equipment before working on it. Use appropriate personal protective equipment. Follow lockout-tagout procedures. Be aware of your surroundings and identify potential electrical hazards. If you are not qualified to work on electrical equipment, call a qualified electrician. Understanding grounding principles is crucial for ensuring electrical safety in any facility. The proper implementation and maintenance of grounding systems can significantly reduce the risk of electrical shock, equipment damage, and fires. Regular inspections, testing, and adherence to the NEC and Institute of Electrical and Electronics Engineers standards are essential for maintaining effective grounding systems. Furthermore, continuous education and training for electrical personnel are vital to ensure that they are aware of the latest grounding techniques and safety practices. By prioritizing grounding, facilities can create a safer working environment and protect their valuable assets. Never take shortcuts when it comes to grounding. Always follow the proper procedures and use the correct materials. Your safety and the safety of others depend on it. Proper grounding provides a low impedance path for fault current, facilitating the operation of overcurrent protection devices like circuit breakers and fuses. The effectiveness of a grounding system depends on the type of soil, its moisture content, and the depth and arrangement of grounding electrodes. The National Electrical Code, or NEC, provides detailed guidelines for grounding requirements, including the types of acceptable grounding electrodes, the size of grounding conductors, and the methods for bonding electrical equipment. The Institute of Electrical and Electronics Engineers, or IEEE, also publishes standards and recommended practices for grounding, particularly in industrial and commercial power systems. Regular inspections and testing of grounding systems are essential to ensure their continued effectiveness. Ground resistance testing measures the resistance between the grounding electrode and the earth, indicating how well the grounding system can dissipate fault currents. Visual inspections can identify signs of corrosion, loose connections, or physical damage to grounding conductors and equipment. Grounding systems should be designed and installed by qualified electrical professionals who are familiar with the applicable codes and standards. Proper grounding is a fundamental aspect of electrical safety and should never be overlooked. By following best practices for grounding, you can protect people and equipment from electrical hazards. The NEC specifies minimum requirements for grounding electrode systems, including the use of metal water pipes, building steel, and ground rods. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Equipment grounding conductors provide a low impedance path for fault currents from equipment back to the service equipment, allowing overcurrent protective devices to quickly clear the faults. Bonding ensures that all metal parts that are likely to become energized are connected together, creating an equipotential plane and minimizing the risk of electrical shock. Ground fault circuit interrupters, or GFCIs, protect people from electrical shock by detecting ground faults and interrupting the circuit. Arc fault circuit interrupters, or RFCIs, protect against fires caused by arc faults, which are unintentional electrical discharges that can occur in damaged or deteriorated wiring. Surge protective devices, or SPDs, protect sensitive electronic equipment from voltage surges caused by lightning strikes, power line disturbances, or other events. Grounding is not a one-size-fits-all solution. The specific requirements for a grounding system will depend on the type of facility, the type of equipment being used, and the local soil conditions. A qualified electrical engineer can help you design a grounding system that meets your specific needs. Grounding is an essential part of electrical safety, protecting people and equipment from electrical hazards. The NEC Institute of Electrical and Electronics Engineers and other standards provide guidance on how to design, install, and maintain effective grounding systems. By following these guidelines, you can create a safer electrical environment for yourself and others.